大家好，这两天我们集中介绍了2024年诺贝尔奖获奖的情况包括大家比较有争议的机器学习呢和神经网络获奖的这个话题。这个话题的中心人物Geoffrey Hinton 呢曾经获得过2018年的图灵奖。当时呢和他一块获奖的还有2位大神，一位呢就是今天我们要介绍的这个 Yann LeCun。说起 Yann LeCun 呢，他在博士后期间曾经跟 Hinton 教授一起做过研究。那这次机器学习和神经网络获奖很多人就感叹为什么 Yann LeCun 没有获奖呢？今天我们就来看看这位大神在 Houston 论坛的发言，关于下一代人工智能，看看他说了什么。在看这视频之前我们先简单介绍一下这位大神。Yann LeCun 呢，这个是在人工智能领域响当当的名字它代表着深度学习的前沿。1960年的7月8号LeCun 出生在法国巴黎郊区的Saucy-Somers-Montmorency他的名字原本拼写为 LeCun 源自古老的布里塔尼亚语。这个名字仿佛预示着他未来在计算机科学领域的深远影响。LeCun 的学习之路呢始于法国1983年呢，他在巴黎欧洲电气工程学院获得工程学位。紧接着呢，他在巴黎的皮埃尔和居里大学，就是后来的索邦大学攻读博士学位，并于1987年获得了计算机科学博士学位。正在攻读博士期间呢， LeCun 就提出了神经网络反向传播学习算法的早期形式，这给日后在深度学习领域的这种突破性工作就奠定了基础。1988年怀揣着对人工智能的热情LeCun 跨越大西洋，加入了美国新泽西州的 AT&T 的贝尔实验室。在这个孕育了众多科技创新的摇篮里边呢， LeCun 开始了他最富创造力的研究生涯。他在这里开发了多项革命性的机器学习方法，其中最著名的莫过于卷积神经网络 CNN。CNN 的灵感来自于生物学中的视觉皮层结构，它彻底的改变了计算机视觉领域，给图像识别技术带来了质的飞跃。LeCun 在贝尔实验室的成就远不止于此他还开发了最佳脑损伤正则化方法和图变换器网络方法。这些技术在手写识别和光学字符识别，就是 OCR 领域产生了深远的影响。值得一提的是呢，他参与开发的银行支票识别系统在1990年代和2000年代初被广泛应用，处理了美国超过10%的支票这无疑是人工智能技术在现实世界中的第一次的重大胜利。1996年LeCun 在 AT&T 实验室升任图像处理研究部的负责人开始致力于的 GPU 图像压缩技术的研究这项技术后来被互联网档案馆众多网站采用，用于分发扫描文档，极大的推动了数字图书馆的发展。在 AT&T 这个工作期间LeCun和 Lemon Bottle 和 Vladimir Vavnik 等杰出的科学家密切合作，这段经历给他日后的研究奠定了坚实的基础。2003年呢，LeCun的职业生涯迎来了新的转折，他加入了纽约大学担任考尔的数学科学研究所和神经科学研究中心雅各布施瓦茨计算科学和神经科学的教授。在 NYU LeCun 的研究重心转向了监督和无监督学习的能量级模型、计算机视觉中的物理识别和移动机器人技术。他的工作不仅推动了学术界的前沿研究，还给实际应用铺平了道路。2012年呢，LeCun成为纽约大学数据科学中心的创始主任，进一步拓展了他在大数据时代的影响力。2013年，他被任命为纽约市原人工智能研究中心的首任主任，这标志着他在学术界和产业界的双重影响力达到了新的高度。LeCun的学术贡献是得到了广泛的认可。2018年他和 Yeshua Bengio 和 Geoffrey Hinton 共同获得了被誉为计算机科学诺贝尔奖的图灵奖，以表彰他们在深度学习领域的开创性贡献。这3位科学家被称为人工智能教父和深度学习教父，他们的工作就奠定了现代人工智能的基础。 那值得一提的是啊，LeCun和 Geoffrey Hinton 的合作呢，尤其引人注目。Hinton 呢，曾经因为他在深度学习的领域呢，刚刚获得了2024年的诺贝尔物理奖，这是人工智能研究首次获得了诺贝尔奖的认可。LeCun和 Hinton 的工作呢，可以说相辅相成，共同推动了深度学习理论和实践的发展。他们的合作不仅体现在学术研究上，还反映在他们对人工智能未来发展的这种共同远景中。那除了学术成就LeCun还积极参与产业界的这种创新。自2013年起他就担任了 Facebook， 就是现在 Meta 的首席人工智能科学家，把前沿化的这种科研转化为实际应用。在他的领导下，Meta 在人工智能领域的投入和成果都达到了新的高度。LeCun的贡献呢，得到了众多荣誉的认可。他是美国科学院、美国国家工程院和法国科学院的院士。他获得了多所著名大学的荣誉博士学位，包括墨西哥国立大学、洛桑联邦学院以及这个法国蔚蓝海岸大学等等。2014年他获得了 IEEE 神经网络先驱奖。2015年呢，获得了帕米杰出科学研究员奖。2022年呢，他和Benjio Hinton 以及Demis Hassabis 一起获得了享有盛誉的阿斯图利亚斯公主奖。2023年法国总统授予他法国荣誉军团骑士勋章，以表彰他对科学和技术的卓越贡献。所以Yann LeCun的职业生涯呢，简直就是人工智能技术发展史的缩影他从早期的这个神经网络技术到卷积神经网络的突破，从学术界的理论创新到产业界的实际应用，LeCun始终站在了人工智能研究的最前沿。他的工作呢，不仅改变了计算机智能研究的最前沿也深刻影响了我们与技术互动的方式那作为 AI 教父之一LeCun继续引领着人工智能未来的发展。他的贡献将在未来几十年内持续的塑造我们的数字世界。好吧，我们今天就开始看他的论坛的视频。
Our next keynote speaker is going to help us see where we are in the journey towards human-level AI. Yann LeCun is the Chief AI Scientist for Facebook AI Research, or FAIR. He's a professor at NYU. He is the recipient of many awards, including a 2018 ACM Turing Award. He's a member of AAAI, National Academy of Engineering. Please join me in welcoming Yann LeCun to the stage.
Thank you, Talia. Yeah, the F in FAIR doesn't mean Facebook anymore.
Oh, I'm so sorry.
It means fundamental. But who cares? Okay, so I'm going to talk about human-level AI, or how do we get there, and how we are not going to get there as well. So first of all, we do need human-level AI because there is a future in which most of us will be wearing smart glasses or wearing other types of devices, and we'll be talking to them, and those systems will host assistants, maybe not just one, maybe a whole collection of them. And what that will cause is that all of us will have basically a staff of kind of smart virtual people working for us. So it's like everybody would be a boss, just not of real humans. And we need to build this for basically amplifying human intelligence and, making people more creative, more productive, and everything. But for this, we need machines that understand the world, they can remember things, that have intuition, have common sense, things that can reason and plan to the same level as humans. And despite what you might have heard from some of the most enthusiastic people, current AI systems are not capable of any of this. So that's what we need, systems that learn to basically model the world, have mental models of how the world works. And every animal has one such model. Your cat certainly has one that's more sophisticated than any AI system ever built or ever devised. Systems that have persistent memory, which current LLMs don't have. Systems that can plan complex action sequences, which is not possible with LLMs today. and systems that are controllable and safe. So I'm going to be proposing an architecture for this that I call objective-driven AI. I wrote kind of a vision paper about this that I posted about 2 years ago. And a lot of people at FAIR are basically working towards implementing that plan. FAIR used to have a combination of, kind of long-term blue sky research and kind of more applied projects. But Meta, a year and a half ago, created a product division called Gen AI, focused on AI products. And they do applied R&D. So now FAIR has been sort of redirected towards the longer term, next generation AI system. We don't do LLMs, basically. The success of AI, including LLMs, including a lot of other systems, over the last 5-6 years, has hinged on a set of techniques that I've called self-supervised learning. And one way to use self-supervised learning, so self-supervised learning consists in training a system not for any particular task, but basically training to sort of represent the input in a good way. And one way to do this is through reconstruction from corruption. So you take, let's say, a piece of text, you corrupt it by removing words or changing some of the words. And it can be text, or it can be DNA sequences or protein or whatever it is, or even images to some extent. And then you train a gigantic neural net to reconstruct the full input, the uncorrupted version. Okay? And that's a generative model because it attempts to reconstruct the original signal. So those, this is meant to be, okay, but it doesn't project. So the red box is like a cost function, right? It computes the distance between the input y and the reconstruction y tilde. And that's what the learning minimizes with respect to the parameters in the system. Now, in the process of doing so, the system learns an internal representation of the input that can be used for all kinds of subsequent tasks. It can be used, of course, to predict words in the text, and that's what happens with autoregressive prediction. So LLMs are a special case of this, where the architecture is designed, oops, and I'm not sure why this thing is flipping by itself. A particular architecture where the thing is designed in such a way that to predict an item, a token, or word, it can only look at other tokens that are to the left of it. It cannot look into the future if you want. So if you train a system to do this, right, you show it a text, and you ask it to predict the next word in the text or the next token. Then you can use the system, of course, to predict the next word. And then you shift that next word into the input, and then predict the second word, and shift that into the input, predict the third word. That's autoregressive prediction. And this is what LLMs do. It's not a new concept. It's been around with us since Claude Shannon, so it goes back to the 50s. That's a long time. But what's changed is that now we have those gigantic neural net architectures that we can train on enormous amounts of data, and it looks like some properties emerge from that. Okay, but that autoregressive prediction has some major limitations. So there's no real reasoning in the usual sense of the term here. And there is another limitation, which is that this only works for data that comes to you in the form of discrete objects, symbols, tokens, words, things that you can discretize, essentially. And we're still missing something big to reach human-level intelligence. And I'm not necessarily talking about human-level intelligence here, but even your cat or your dog can do amazing feats that are still completely out of reach of current AI systems. How is it that any 10-year-old can learn to clear up the dinner table and fill up the dishwasher? And the 10-year-old can learn this in one shot, right? There's no need to practice or anything. 17-year-old can learn to drive a car in about 20 hours of practice. We still don't have level 5 self-driving cars. And we certainly don't have household robots that can clear up the dinner table and fill up the dishwasher. So we're really missing something big, right? Otherwise, we would be able to do those things with AI systems. So we keep bumping into this thing called the Moravec paradox, which is that things that appear trivial to us, that we don't even consider intelligent, seem to be really, really difficult to do with machines. But like high-level, complex, abstract thinking, like manipulating language, seems to be easy for for machines, or things like playing chess and Go and stuff like that. Okay, so maybe one reason for this is the following. An LLM is typically trained on 20 trillion tokens. A token is basically is like 3/4 of a word on average for a typical language. So that's 1.5 10 to the 13 words. Each token is about 3 bytes, typically. So that's 6 10 to the 13 bytes. It would take, on the order of a few 100,000 years for any of us to read through this, right? That's the totality of all the text available publicly on the internet, essentially. But then consider a human child. A human child, a 4-year-old, has been awake a total of 16,000 hours, which, by the way, is 30 minutes of YouTube upload. We have 2 million optical nerve fibers, optic nerve fibers coming to our brain. Each fiber roughly carries about 1 byte per second. Maybe it's 1/2 byte per second. Some estimate has said it's like 3 bits per second. Doesn't matter. It's an order of magnitude. So that data volume is about 10 to the 14 bytes. Roughly the same order of magnitude as the LLM. So in 4 years, a child has seen as much visual data as the biggest LLM trained on the entire publicly available text on the internet. So that tells you a number of things. That tells you, first, that we're never going to reach anything close to human-level intelligence by just training on text. That's just not going to happen. Then the counter-argument is, okay, but visual information is very redundant. So first of all, this 1 byte per second per optic nerve fiber, that's already a 100-to-1 compression ratio compared to the photosensors you have in your retina. We have on the order of 60 to 100 million photosensors in our retina, and that gets compressed using neurons in front of your retina to 1 million nerve fibers. So there is already a 100-to-1 compression. Then it gets to the brain, and then it's expanded by a factor of 50 or something like that. So I'm measuring compressed information, but it's still very redundant. And redundancy actually is what self-supervised learning requires. Self-supervised learning will only learn something useful from redundant data. If the data is highly compressed, which means it's completely random, you can't learn anything. You need redundancy to be able to learn anything. You need to learn the underlying structure of the data. So we're going to have to train systems to learn common sense and physical intuition by basically watching videos or by living in the real world. I'm going to maybe go a little bit out of order and then tell you a little bit about what this objective-driven AI architecture really is. And it's quite different from things like LLM or feed-forward neural nets in the sense that the inference procedure is not just running through a bunch of layers of a neural net, but it's actually running an optimization algorithm. So conceptually, it looks like this. A feed-forward process is a process by which you see an observation, run through perception system, for example, a bunch of layers of neural net, and produce an output. You can only have one output for any single input. But there are a lot of situations for which there are multiple possible outputs, interpretations for a percept. And you'd like a process that does not just compute a function, but computes a mapping that might have multiple outputs for a single input. The only way you can do this is through implicit functions. Basically, a function like this objective here, the red box on the right, which basically measures the compatibility between the input and a proposed output, and then computes the output by finding one value of the output that is most compatible with the input. And you can do this by imagining that this objective is some sort of energy function, and you're minimizing this energy with respect to the output. You might have multiple solutions. You might have some way of going through those multiple solutions. The human perceptual system does this. If you have multiple interpretation of a particular percept, your brain spontaneously will actually cycle through those interpretations. So there's some evidence that things of that type can take place. But let me go back to the architecture. So using this principle of inference by optimization, the way, the hypothesis of the way people think, if you want, is the following. You make an observation in the world. A perception system gives you an idea of the state of the world, the current state of the world. But of course, it only gives you an idea of the state of the world you can currently perceive. You might have some idea about what the rest of the state of the world is from memory. So that might be combined with the content of a memory. And that's fed to a world model. What is a world model? A world model is your mental model of how the world behaves. Okay, so you can imagine a sequence of actions that you might take. And your world model will allow you to predict what the effect of the sequence of action will be on the world. So the green box, the world model, you feed it a hypothesized sequence of actions, and it predicts what the end state of the world is going to be, or it predicts the entire trajectory of what's going to happen in the world. You feed this to a bunch of objective functions. One objective that measures to what extent a goal has been achieved, a task has been fulfilled, and maybe a set of other objectives that are guardrails, things that basically measure to what extent the trajectory that has been followed or the actions that have been taken are things that are not dangerous for people around the robot or the machine, etc. So now the inference process, I'm not talking about learning yet, it's just inference, consists in finding the action sequence that minimizes those objectives. Finding a sequence of actions that minimizes those objectives, okay? That's the inference process. So it's not just feed-forward. You can do this by, searching through discrete options, but that's inefficient. A much better way is to make sure that all of those boxes are differentiable and you backpropagate gradient through them and you update the action sequence through gradient descent. Now this idea is very, very far from being new. It's over 60 years old, if not more. And it's based on, okay, so first let me talk about the advantage of doing this kind of inference using a world model. The advantage is that you can basically accomplish new tasks without requiring any learning. We do this all the time. We're faced with a new situation. We think about it. We imagine the consequences of our actions. And we take the sequence of actions that will fulfill our objectives, whatever it is. We don't need to learn to accomplish that task. We can plan. Okay, so this basically is planning. You can reduce most forms of reasoning to optimization as well. So this process of inference by optimization is intrinsically more powerful than just running through a bunch of layers in a neural net. Now this idea that you do inference by optimization is, as I said, has been around for over 60 years. In the optimal control theory field, it's called model predictive control. You have a model of the system you're trying to control, let's say a rocket or something, or an airplane, and or a robot, and you can imagine, you can compute using your world model the effect of a sequence of controls, commands, and then you optimize the sequence so that the motion does what you want. All classical robotics, motion planning is done this way, okay? Not a new thing. What's new here is we're going to learn the world model, and we're going to learn the perceptual system that is going to extract an appropriate abstract representation of the situation, of the world. Now, out of this, before I go into an example of how this can be run, you can build an overall kind of AI system that has all of those components, the world model, the cost functions that can be configured for the task at hand, the actor, which is the module that really optimizes, finds the optimal sequence of actions given the world model, the short-term memory, perception system, etc. So how does that work? So if your action is not a single action, but an action sequence, and your world model is really a system that tells you, given the state of the world at time t and an action I might take, predict the state of the world at time t plus 1. And you want to predict what a sequence of two actions, in this case, will produce. You can run your world model multiple times, right? So here it's represented as unfolded in time. Get the initial world state representation, feed a hypothesis for action 0, use a world model to predict the next state of the world, Then action 1, next state of the world, compute the cost, and then through backpropagation and gradient-based optimization method, figure out the 2 actions that will minimize the cost. Okay? That's model predictive control. Now, the world not being completely deterministic in general, you might have to use latent variables to feed to your world model. So latent variables are basically variables that can swipe over a set or be drawn from distributions, and they represent, they basically cause the world model to swipe through multiple predictions that are compatible with the observation. The world is not entirely predictable, and so you might need to deal with this type of uncertainty when making predictions. What's more interesting is to do what humans seem to be capable of doing, and certainly a number of animals, and it's hierarchical planning. So if you're planning a trip from, let's say, New York to Paris, you could be using your world model, the model of your own body, and maybe your idea of the entire configuration of the world from here to Paris, to plan your entire trip in terms of your low-level muscle control. But of course, nobody does that. You can't do it. You don't even have the information to do it. And it would be kind of crazy, right? The number of steps every 10 milliseconds of muscle control that you have to do before you go to Paris, is just insane. So what you do is you plan hierarchically. You go at a very high level, and you say, well, to go to Paris, I first need to go to the airport and catch a plane. How do I go to the airport? I'm in New York City, let's say. I have to go down in the street and hail a taxi. How do I go down in the street? Well, I have to raise from my chair, move to the door, open the door, go to the elevator, push the button, blah, blah, blah. How do I get up from my chair? At some point, you're going to have things that can be expressed in terms of low-level muscle control actions. But we're not planning the entire thing in terms of the low level. We're doing hierarchical planning. How to do this with AI systems is completely unsolved. We have no idea how to do this. And that seems like a pretty big requirement for intelligent behavior. So, how are we going to learn world models that are hierarchical, work at several different levels of abstraction, and allow us to do this kind of hierarchical planning? Nobody has demonstrated anything close to this. That's a big challenge. Yeah, it's just a pictorial representation of the example I just said. Okay, so how are we going to train this world model now? Because that's really kind of the big challenge. And you look at babies, but this is true for animals as well. And psychologists, cognitive scientists, I've tried to figure out at what age babies learn basic concepts about the world, like how do they learn, intuitive physics, physical intuition, all that stuff. This happens long before they start to learn about language and interaction and things like this. So things like face tracking happen really, really early, biological motion, the fact that there is a difference between animate and inanimate object, that happens pretty early too. Object permanence happens really early. The fact that when an object is hidden by another one, it still exists. And then, babies learn like natural kinds of categories. You don't need to give them names of things. They will know that a chair and a table and a cat are different. Stability and support. But things like gravity, inertia, conservation of momentum, that actually only pops up around 9 months, roughly. That takes a long time. So if you show a 6-month-old the scenario on the left here where a little car is on a platform and you push it off the platform and it appears to float in the air, 6-month-old baby will barely pay attention. A 10-month-old baby will go like the little girl. She's understood that it shouldn't happen. The object should fall. And when something surprising happens, that means your world model is wrong, so you pay attention. Because it could kill you. So the type of learning that needs to happen here is very similar to the type of learning that we were talking about earlier. Okay? Take an input, corrupt it in some way, and train a big neural net to predict what's missing. If you train a system to predict what's going to happen in a video, the same way we train neural net to predict what's going to happen in text, maybe those systems will be able to learn common sense. The bad news with this is that we've been trying to do this for 10 years, and it's a complete failure. Okay? We've never been able to get anywhere close to systems that really learn any kind of, kind of generic knowledge about the world by just trying to predict the pixels in a video. You can train a system to predict videos that look nice, and there are a number of examples now of, video generation systems. But internally, they are not good models of the physical world. They cannot use them for that. Okay, so this idea that we're going to use generative models to predict what's going to happen in the video and the system will magically understand, the structure of the world, complete failure. And we tried many things over 10 years. The reason it's a failure is because there are many possible futures. And in a discrete space like text, you cannot predict which word is going to follow a sequence of words, but you can produce a probability distribution of all possible words in a dictionary. But when it's video frames, we do not have a good way to represent probability distributions over video frames. And in fact, the task is completely impossible. Like if I take a video of this room, right? I take a camera, I shoot that part, and then I stop the video and I ask the system to predict what's next in the video. It might predict that there's going to be the rest of the room. At some point, there's going to be a wall. There's going to be people sitting. The density is probably going to be similar to what's on the left. But it cannot possibly predict at the pixel level what all of you look like, what the texture of the wall looks like, and the precise size of the room and all things like that. There's no way you can predict all those details accurately. So the solution to this is what I call joint embedding predictive architectures. And the idea is to just give up on predicting pixels. Instead of predicting pixels, let's learn a representation, an abstract representation of what goes on in the world, and then predict in that representation space. Okay? So that's the architecture, joint embedding predictive architecture. There's two embeddings. Take X, the corrupted version, run it through an encoder. Take Y, run it through an encoder. And then train the system to predict the representation of Y from the representation of X. Now the question is how you do this, because if you just train a system like this using gradient descent backpropagation to minimize the prediction error, it's going to collapse. It's going to learn a representation that is constant, and now it becomes super easy to predict, but it's not informative. But that's the difference that I want you to remember, the difference between generative architectures that try to reconstruct predictors, autoencoders, generative architectures, masked autoencoders, whatever, and then the joint embedding architecture where you make predictions in representation space. The future, I think, is in those joint embedding architecture. We have tons of empirical evidence that to learn good representations of images, the best way to do it is to use those joint embedding architectures. All attempts at trying to learn representation of images using reconstruction are bad. They don't work very well. And there were huge projects on this and claims that they work, but they really don't. The best performance are obtained with architecture on the right. Now, if you think about it, this is really what we do with intelligence. Finding a good representation of something or phenomenon so that you can make prediction is really the essence of science, really, right? Like think about the fact that if you want to predict the trajectory of a planet is a very, very complex object. It's enormous. It's got weather and temperature and, density and all kinds of things you can measure about a planet. It's maybe an incredibly complex object. But to predict the trajectory of a planet, you only need to know 6 numbers, 3 positions and 3 velocities. That's it. You don't need to know anything else. So that's a really kind of important example to really demonstrate the fact that the essence of the ability to predict really is to find good representations for things we observe. So how do we train those things? So this is okay, how do we train those things? So you want to prevent the system from collapsing. So one way to do this is to have some sort of cost function that measures the information content, if you can, of the representation coming out of the encoder, and try to maximize the information content or minimize the negative information, which is what's written here. So you're training a system to simultaneously extract as much information from the input as possible, but at the same time, to minimize the prediction error in that representation space. So the system is going to find some sort of trade-off between extracting as much information as possible, but not extracting information that is not predictable. Okay? You're going to get like a good representation in which space in which you can make predictions. Now, how do you measure information? And that's really where things become a little weird. Okay, I'm going to skip this. Well, there is a way to understand this mathematically in terms of training energy-based models and energy functions, but I don't have time to go into this, but basically I'm telling you a number of different things here. Abandon generative models in favor of those JEPA architectures, abandon probabilistic models in favor of those energy-based models, abandon contrastive methods. I didn't talk about this because I'm going to come to this in a second, and also reinforcement learning, but I've been saying this for 10 years. And so these are all four most popular staples, pillars of machine learning today, so I'm not very popular at the moment. Okay, so one way to do this is to have some estimate of the information content that comes out of an encoder. And there is half a dozen different methods for doing this at the moment. There's one actually missing here called MMCR from my colleagues at NYU and Flatiron, actually. So one idea here is prevent the system from just collapsing and producing constants, right? So take the variables that come out of the encoder and make sure that those variables have non-zero standard deviation. You can put this in a cost function over a batch of samples, make sure that the weights are such that the variables don't collapse and become constant. That's easy enough. Now, the problem is that the system can cheat and make all the variables equal or very highly dependent or correlated. So what you have to do is add another term that says, I want to minimize the off-diagonal terms of the covariance matrix of those variables to make sure that they're correlated. And of course, that's not enough because the variables could still be dependent, dependent but not correlated. So we use another trick, which is to expand the dimension of Sx into a higher dimensional space Vx, and then apply this variance-covariance regularization in that space. And that seems to be enough. But there is a trick, like I fooled you, or some of you, because what I'm maximizing here is an upper bound on information content. And I'm crossing my fingers that the actual information content will follow my maximization of the upper bound. What I would need is a lower bound. So I would push up on the lower bound and the information would go up. Unfortunately, we don't have lower bounds on the information. Or at least we don't know how to compute it if we have them. There's a second set of methods. It's called distillation style methods. And that method works in mysterious ways. If you really want to have a clear explanation for why it works, you should ask Surya Ganguly, who is sitting right here. He has a paper on this. Personally, I'm dumbfounded, but it works really well. And it consists in only updating one half of this architecture and not backpropagating gradient on the other half and then sharing the weights in a funny way. There's a bunch of papers on this. It works really well if you want to train a system completely self-supervised to learn good representations of images. This is as good as any. And where the corruption of the images is by masking. We have some more recent work where we do this for video, so we can train a system to basically extract good representations of video that we can use for a downstream task in action recognition in video and things like this. And it consists in taking a video, masking a big chunk of it, running through this thing, and doing prediction in representation space and using this distillation trick to prevent collapse. And this works really well. Okay, so in the future, all of our interaction, if we succeed in this program and eventually get to systems that can reason, can plan, can understand the physical world, it's going to take years, right, before we get everything here to work, if not a decade. Mark Zuckerberg keeps asking me how long it's going to take. So if we succeed in doing this, okay, we're going to have systems that really will mediate all of our interaction with the digital world. They will answer all of our questions. They will be with us at all times. They will basically constitute a repository of all human knowledge. And this feels like an infrastructure kind of thing, like the internet, right? It's not like a product, it's more like an infrastructure. These AI platforms must be open source. I don't need to convince anybody from IBM here because IBM and Meta are part of something called the AI Alliance, which promotes open source AI platforms. But, and I really thank Dario for spearheading this and everybody at IBM. So we need those platforms to be open source because we need those AI systems to be diverse. We need them to understand all languages in the world, all cultures, all value systems. And you're not going to get that out of a single assistant produced by a company on the West Coast or the East Coast of the US. This will have to be contributions from the entire world. And of course, it's very expensive to train a foundation model, so only a few companies can do this. So if those companies like Meta can provide those base model in open source, then the entire world can fine-tune them for their own purpose. So that's kind of the philosophy that Meta has adopted and IBM as well. So open source AI is not just a good idea, it's necessary for cultural diversity, perhaps even the preservation of democracy. Training and fine-tuning will be crowdsourced or will be done by the ecosystem of startups and other companies. And this is really what has jump-started the ecosystem of AI startups, is the availability of those open source AI models. How long is it going to take to reach human-level AI? I don't know. Could be years to decades. There's a huge variance. And there's many problems to solve on the way, and it's probably almost certainly harder than we think. It's not going to happen in one day. It's going to be like progressive evolution. So it's not like one day we're going to discover the secret to AGI and we're going to turn on a machine and immediately we'll have super intelligence and all of us will be killed by a super intelligent system. No, it's not happening this way. Machines will surpass human intelligence, but they will be under our control because they will be objective driven. We give them goals and they fulfill those goals. It's just like many of us here are leaders in industry or academia or whatever. We work with people who are smarter than us. I certainly do. There's a lot of people working with me who are smarter than me. Doesn't mean they want to dominate or take over, right? So that's the story. There is risk, but I'm going to leave that for the question session. Thank you very much.
好的，哎呀，听的开始有点困啊，后来呢坚持了一下啊，听课都是这样的。对于Yann LeCun的这次演讲啊，就是不仅总结了在人工智能领域当前的这个状态，更是给未来的研究方向指明了道路。那作为深度学习的这个先驱之一LeCun的观点呢，对整个 AI 社区都具有重要的这种指导意义。我们来总结一下他的主要观点看看他的这些见解对未来 AI 研究可能产生怎么样的影响。首先LeCun强调了当前 AI 系统的局限性特别是在理解物理世界和进行复杂推理方面的不足。他指出尽管大语言模型在处理文本数据方面取得了显著进展，但是他们仍然缺乏真正的理解能力和常识推理。这个观点就提醒我们呢，尽管 AI 已经取得了令人瞩目的成就，但是距离真正的人工智能还有很长的路要走。那LeCun呢还提出了一个关键挑战，是分层规划能力。人类能够轻松的在不同的抽象层次上进行规划，从高层目标到具体行动，而当前的 AI 系统无法实现这种灵活性。这个观察力呢就为我们未来的 AI 研究提供了一个重要方向，开发能够像人类一样进行多层次灵活规划的 AI 系统。另外一个重要观点呢，就是关于世界模型的学习。LeCun强调婴儿从很小就开始学习基本的物理概念和世界模型。这种学习呢发生在语言习得之前。这一观察 启发了我们的思考，就是如何设计 AI 系统，使它能够通过观察和交互来学习基础知识，而不是仅仅依赖于预编程的规则和大规模的这种文本数据。LeCun 呢还批评了仅通过预测视频像素来学习世界模型的这种方法。他认为这种在过去10年中已经失败了。那相反他提出联合嵌入预测架构 JEPA 作为一种新的方法。JEPA 它旨在学习世界的这种抽象表示，然后呢，在这个表示空间中进行预测，而不是直接预测像素。所以这个思路呢，可能会引导未来的 AI 研究朝着更抽象、更高效的这种表示学习方向发展。LeCun还强调了开源 AI 平台的重要性。他认为呢，为了确保文化多样性和广泛的贡献 ，AI 技术应该开放。所以这个观点对 AI 未来的发展也具有很大的影响。它可能会推动更多的这种协作研究，促进 AI 技术的这种民主化，并帮助解决 AI 偏见和不公平这些问题。关于 AI 发展的时间线LeCun预测呢， AI 不会突然到达超人类的水平，而是会逐步发展。它可能需要数年到数十年的时间。这种谨慎而比较现实的预测呢，是有助于平衡公众对 AI 的期望同时呢，也给研究人员和政策制定者提供一个时间的框架，以便他们呢可以做出长期的规划。那LeCun还提出即使人类超越了即使 AI 超越了我们人类他们仍将受到控制，因为他们是目标驱动的。这个观点对于缓解我们老百姓对于 AI 失控的这种担忧也具有重要意义，同时呢，也给 AI 未来的研究提供了一个比较重要的思考方向。所以呢，这次演讲呢LeCun呢给 AI 演讲这个社区提供了一个全面的路线图就是他指出当前研究的这种局限性，然后呢提出了新的研究方向，同时他也强调负责任和包容性的 AI 发展的这种重要性。所以这些见解呢，可能会在未来几年内深刻影响到 AI 的这种研究方向和重点。那我们根据他的演讲可以预测呢，在未来的 AI 研究可能会更加关注以下几个方面。第一，就是开发能够学习抽象世界模型的 AI 系统。第二个呢，就是探索分层规划和复杂推理的新方法第三呢，就是研究如何将物理直觉和常识知识整合到 AI 系统中。第四呢，就是推动开源 AI 平台的发展，促进全球的协作。最后呢，就是加强 AI 的安全和伦理的研究，确保 AI 技术它负责任的发展。所以 LeCun 的观点呢，就提醒我们，尽管 AI 技术发展迅速，但呢，实现真正的人类级的这种 AI 还是一个长期的目标这要研究人员、政策制定者和公众的保持耐心同时呢，继续投资基础研究和负责任的这种 AI 发展。好吧，这就是这位大神给我们世界指明的道路，准不准？有生之年拭目以待吧。再会。